Good morning to all. Today we are discussing about emitter coupled logic. Introduction. Emitter coupled logic is a bipolar non-saturated transistor type logic. It means that the bipolar logic family can be classified into two types, that is the saturated bipolar logic family and a non-saturated bipolar logic family. So this emitter coupled logic is belonging to non-saturated bipolar logic family. Okay, and next point, in this emitter of transistors are joined together. Difference amplifier is a basic circuit of emitter coupled logic. Mean that in this circuit we are using the two transistors, that is Q1 and Q2, and these two transistors emitter terminals are cascaded to form a emitter coupled logic. Okay, so this emitter coupled logic circuit, when the transition from one state to the other state, this emitter coupled logic circuit is acting as differential amplifier. So this differential amplifier is to draw the constant current from the power supply, and noise and spikes are not produced. So that is the reason compared to other families we are using the emitter coupled logic. Okay, and third point, in addition, the transistors are operated in the cutoff and active regions. So transistors do not go into saturation, and as a result, turn off time is reduced. It means that in this intercoupled logic, all the transistors are operated in either cutoff region or active region. So these transistors are not entered into saturation region. Therefore, the storage time is minimized. Then the switching speed of the circuit is increases. Then the delay is minimized. Okay. And next point, in ECL type logic, propagation delay is about 1 nanosecond, which is the smallest of all types of logics. It means that compared to all other logic families, the emitter coupled logic have very less propagation delay. Okay, and next point, in this logic power distribution is more as the transistors are operated in the active region. It means that compared to all other logic families, this emitter coupled logic family is require more power because all the transistors are operated in the active region. Okay, here now we are discussing about two input ECL or NOR gate as shown in figure. Okay, so this is the circuit diagram of a two input ECL or NOR gate. Okay, so this emitter coupled logic is giving the two outputs. That is, one is the OR and the other one is the NOR. Okay, so here the complementary gates are provided with the help of transistor T2 and T3, which form the basic differential amplifier circuit. Mean that here the T2 and the T3 transistors we are considered as complementary gated transistors. It means that one transistor is on and the other transistor is off. Okay, so these two gives them complementary outputs. Okay, and when the transition from one state to the other state, these two transistors acts as a differential amplifier circuit. Okay, and the next point, input of OR NOR gate are provided through T1 and T2 transistors. It means that in this two input ECL OR NOR gate, the inputs are given to the base terminals of the T1 and T2 transistors. Okay, and the next point, for balancing the voltage level between inputs and outputs, emitter follower stage is used. Okay, so this is we are considered the emitter coupled circuit. Okay, so at the collector terminals of the T2 and T3 we are collected the output, but here this emitter coupled circuit does not give the accurate output signal. Okay, so these signals are interrupted by the noise. So we are avoiding this noise signal. These corresponding outputs are given to the other transistors. Okay, and these transistors are act as emitter followers because we are connected the output at the emitter terminals of the T4 and T5 transistors. Okay, and next point, transistor T4 and T5 work as emitter follower transistor and output are taken from their emitters. So, with help of this T4 and the T5 transistors, we are avoiding the noises in the output signal, and these two transistors are acting as emitter followers for we are correcting the output at the emitter terminals of these two transistors. Okay, and next point T5 gives output Z for NOR gate while T4 gives output Z complement for OR gate. So the emitter terminal of the T4 transistor gives the OR gate output and the emitter terminal of the T5 transistor gives the NOR gate output. Okay, and here the input voltages are negative and the transistor T3 has fixed negative voltage, that is we are considering minus 1.32 volts, which is useful for comparison with the input voltages. It means that in this emitter coupled logic circuit, the base terminal of this T3 transistor value is minus 1.32 volts. Okay, so always this voltage is compared to the this input stage voltage. So with respect to this comparison, this emitter coupled circuit gives the output. Okay, and now we are discussing about operation of two input ECL or NOR gate. Okay, in the ECL logic, minus 1.7 volts is taken as a logic 0 and minus 0.8 volts consider the logic 1 level. It means that in the last classes we are assuming the logic 0 equal to 0 volts and logic 1 is 5 volts. But in the ECL logic, we are consider the logic 0 is minus 1.7 volts and logic 1 is minus 0.8 volts. Okay, and here we are studying the two input ECL logic, right? Therefore, we got the four possible combinations. That is, first one is for A and B is equal to 0, T1 and T2 are off, so T5 conducts and gives output to logic 1. At the same time, T3 conducts, so T3 is on and T4 gives output as logic 0. It means that in the two input ECL logic, we are consider them both the inputs are 0 0. We know that the logic 0 input voltage we are consider the minus 1.7 volts. Okay, and this base terminal of the T3 transistor we are apply the voltage is minus 1.32 volts. Okay, now we are comparing this voltage with the input stage voltage. Okay, so minus 1.32 volts is greater than the minus 1.7 volts. Therefore, these T1 and T2 transistors are off. Okay, so from the power supply, here we got the logic 1 is output. This output is given to input of this T5 transistor and the T5 transistor is operated in the saturated region. Therefore, here we get the output is logic 1 output. Okay, and the T3 transistor is operated in the saturation region. Okay, so from the power supply to ground from a short circuit. Okay, so at that time the connector terminal of this T3 transistor is logic 0, that output is given to the base terminal of this T4 transistor. Therefore, the sufficient voltage is not given to the base terminal of this T4 transistor. This transistor is operated in the cutoff region. Okay, so the output of the T4 transistor is logic 0. Okay, so already we are considered the output at the emitter terminal of this T4 transistor. Then we got the output is logic 0 output. Okay, now once we are verified the truth table of OR NOR gate, both the inputs are 0 0. The OR output is 0 and NOR output is 1. Okay, so here we are considered the NOR output is logic 1 and OR output is logic 0. Okay, and the next possible combination of input is for A and B is equal to 1, T1 and T2 are on, so voltage drops across them and T5 receives the no current supply in its base and T5 remains off, while T3 is off due to lack of sufficient voltage and T4 become on gives output as logic 1. Mean that in this circuit we are applying the both the inputs are logic 1. We know that the logic 1 voltage is minus 0.8 volts, and already we mentioned the base terminal of this T3 transistor is minus 1.32. Okay, so minus 1.32 is less than the minus 0.8. Okay, at that time this T3 transistor is operated in the cutoff region. Okay, so from the power supply, here we got the output is logic 1, that output is given to input of this T4 transistor. Okay, so the sufficient voltage is given to the input of this T4 transistor, the transistor is on, and finally we got the output is logic 1 output. Okay, and the T1 and T2 transistors are on with respect to this input voltage. Okay, so here form a short circuit. Okay, from the power supply to ground form a shortest path. Okay, therefore here we got the output is logic 0 output. So this logic 0 output is given to input of this T5 transistor, and this T5 transistor is operated in the cutoff region. Okay, so here we got the output is logic 0 output. Okay, and now we are verify the truth table of the or NOR gate. Both the inputs are 1 1, the output of the OR is 1. So here we get the output equal to logic 1, and the NOR output is logic 0. So here we get the output equal to logic 0. Okay, and the next possible combination of the input is any one of the input is high and the other input is low. That is, for A or B is equal to 1. The T1 or T2 transistors are on, so voltage drops across them, and T5 receives the no current supply in its base, and T5 remains off while T3 is off. Due to lack of sufficient voltage, and T4 becomes on, gives output as logic 1. It means that in this circuit we are giving any one of the input is high and other input is low. For example, here we are assuming the A transistor, T1 transistor input is logic 0 and T2 transistor input is logic 1. We know that the logic 0 voltage is minus 1.7 volts, and logic 1 voltage we are consider the minus 0.8 volts. Okay, at that time minus 1.7 volts is less than minus 1.32, therefore this T1 transistor is off, and this minus 1.32 is less than the minus 0.8, therefore this T3 transistor also off, but this T2 transistor is on. Okay, here exists a short circuit path from the power supply to the ground. So at that time the connector terminal of this T2 transistor got the logic 0 output. The logic 0 output is given to the input of this T5 transistor, and this T5 transistor is off. Okay, and finally we got the output is logic 0 output, and this T3 transistor is also off. From the power supply, the connector terminal of this T3 transistor got the logic 1 output. This logic 1 output is given to the base terminal of this T4 transistor, and with respect to the sufficient base voltage, the T4 transistor is on, and finally we got the output is logic 1. Okay, and once we are verify the truth table of the OR NOR gate, any one of the input is high. Okay, the OR output is 1 and an NOR output is 0. So here any one of the input is high, we got the output of the OR gate is logic 1, and output of the NOR gate is logic 0. So in this way, with help of the intercoupled logic, we are realize the OR NOR gate and AND gates. Okay, thank you.